Hello students, now here in this video we have to start the chapter 3, that is functions of number theory. Functions of number theory. So in that one we have to see a very first function, that is the greatest integer function. The greatest integer function. Now what is the definition of it? Let's see the definition. And greatest integer function is a function, it is denoted by this square bracket, is a function from set of real number to set of integers and is defined as that this, suppose the greatest integer function of x, then this is nothing but the greatest integer less than or equal to x. Now for example, now look at here, suppose the x is 1.5. So we have to take, here codomain is set of integers. So this is a real number. So we have to take such a integer is the answer here, which is the less than or equal to x. Either it is equal to or less than x, but it should be an integer. So if you see a number line, suppose here 0, 1, here 2 suppose, so here 1.5. So less than or equal to x, if it will be an integer, it will satisfy this equal to. If it is not integer, now this is not integer, so it is less than that. So here we get it is what the value here, it is 1. Again let's see the next example. Suppose I am taking 1.9, then also here 0, 1, 2, so 1.9 is somewhere here, so it is not equal to any integer, so it is less than that, so this is also 1. Now if I am taking 0.1 is somewhere here, so what is it? Its value is 0. The greatest integer function of 0.1 is 0. If I am taking minus 1.5, now look at it carefully, minus 1.5, suppose here minus 1, here suppose minus 2, so minus 1.5 is here, fine. Now we want the integral value which is less than this real number. So less number will be on left hand side, not on right hand side. This minus 1 will be a greater number while the minus 2 is the least number. So here what is the answer? Here it will be minus 2. Fine. Similarly, the next one, look at for some more examples. Let's we take. Suppose the next one will be minus 1.9. Still its greatest integer function is how much? Minus 2. Suppose I am taking e having value 2.78 something. So its greatest integer function is how much? 2. Suppose I am taking pi. What is the value of pi? It is 3.14 and so on. So its greatest integer function is 3. But if I am taking minus pi, then its greatest integer function is minus 4. Now similarly for minus e, if I am taking -e, then its greatest integer function will be -3. Again, if we will take integral value, then its greatest integer function is the value itself equal to that one for integral value. And if I am taking minus 3, then also it is minus 3, as these are what? Integers. These are all not integers, these are rational, so they are great. For positive we take the least one, and for the negative we will take again the least than that. Fine. Everywhere we get a less than that one. Fine. Now let's write one remark here. That remark is also important. Remark. Given any real number x, given any real number x, we can write x equal to that greatest integer function plus some number, where 0 less equal mu less than what? 1. Now look at here, if I will take 1.5, this 1.5 can be written as 1 plus 0.5, and you know the greatest integer function of 1.5 is nothing but 1. So if this is x, then this 1 is nothing but its greatest integer function, plus this part I am taking as mu. So this mu is what? It is greater equal 0 but less than 1. This is less than 1 always, but it may be equal to 0. If I am taking 2, then 2 can be written as 2 plus 0. That time this mu will become 0. Fine. So for any real number x, we can write that real number as such, as this x equal to greatest integer plus some number, some non-zero number, where this x is what? Is called as integral part of x, and this mu is called as fractional part of x. Now let's see the theorem, or you can say the properties of greatest integer function. So we will take them as a theorem. So theorem, let x, y are the real numbers, then first greatest integer function of x is less equal x less than the greatest integer function of x plus 1. Again, x minus 1 is less than greatest integer function of x less equal to x. Again, 0 less equal x minus greatest integer function of x less than 1. We will write one by one the properties and we will prove them. So let's see the proof of this one. Suppose the proof. Okay. So now let x belongs to R, then x is a real number, then x can be written as the greatest integer function of x plus mu, where this mu is what? Lies between this interval, close 0, open 1. Fine. Now since mu is greater equal 0, this x is greater equal this greatest integer function. This is positive. So this part, if we remove this mu from here, then this will become a greater. Fine. This is a greater. For all x belongs to set of real number. Call it as equation number 1, suppose. Also, if mu is less than 1, means this part, less than 1, then we get x equal to, or mu less than 1, we can say this implies if we add in greatest integer function on both sides. So mu less than greatest integer function plus 1. Now greatest integer function is some value, and at time this inequality remains same. Most probably the inequality remains same. Fine. Now if we check, this part is nothing but our x. This is our x. So this is x less than whom? Greatest integer function plus 1. Call it equation number 2. So from 1 and 2, if you check, x is greater equal this, but x is less than this. So we get this result. If we combine them from 1 and 2, we get this greatest integer function is less equal x and less than greatest integer function plus 1. This is the result. Now by 2, we get, from 2, we get x minus 1 is less than greatest integer function. But this greatest integer function that gives x minus 1 is less than greatest integer function, and which is what? Less equal whom? X. This is from 1. This is from 1, and this is another result. This is first result, and this one is here. Fine. Now by 1, 0 less equal x minus greatest integer function. If we take this, subtract greatest integer function, we will get this part. Fine. But what is this? This is equivalent to, what is x? X is greatest integer function plus mu minus greatest integer function. So this is equivalent to whom? This is equivalent to mu, and that is what? Less than 1. Here it is less than 1. Fine. Therefore we get 0 less equal this part less than what? 1. This one less than 1. X minus greatest integer function is less than what? 1. That is our third part. This is our third part we have been proved in this first one. Fine. Now let's see the second property. The second property. Second property says the greatest integer function is summation 1. I goes from 1 to x. So proof of this, it is a very simple thing we can write. The summation 1 I from 1 to x. Fine. Count the number of positive integer less than or equal to x, that is summation 1 I from 1 to x equal to this greatest integer function of x. Now let's see the third part. Greatest integer function of x plus greatest integer function of y is less equal, greatest integer function of x plus y is less equal greatest integer function of x plus greatest integer function of y plus 1. Okay. Now look at here. Proof. Let x and y be any real number. Any real number. Then x will be a greatest integer function of x plus mu1, where mu1 is 0 less equal mu1 less than what? 1. That is x equal to, suppose, n plus mu1. We will name greatest integer function as n here. Fine. And y equal to greatest integer function of y plus mu2, where 0 less equal mu2 less than 1. That is y equal to, suppose, m plus mu2. We are naming here reason we can say greatest integer as greatest integer function of x we assume n and greatest integer function of y we assume m. Okay. Therefore, the greatest integer function of x plus greatest integer function of y is how much? N plus m. If this from this, so call it as equation number 1. Now what about x plus y? What is x plus y? Is n plus m plus mu1 plus mu2, where 0 less equal mu1 mu2 is less than 1, and these n m are what? The integers. N and m are integers. Therefore, we get x plus y is what? Greater equal n plus m. Therefore, the greatest integer function of x plus y is also what? Greater equal to n plus m. Therefore, x plus y, the greatest integer function of x plus y is also greater equal greatest integer function of x plus greatest integer function of y. Call it as equation number 2. Fine. Now as x plus y equal to n plus m plus mu1 plus mu2, so that gives us the greatest integer function of x plus y is equal to n plus m plus greatest integer function of whom? mu1 plus mu2. Why does this? Because n and m are integers, so their addition is also integer, and the greatest integer function of n plus 1 will remain same, as this is what? Integer. Fine. Therefore, what does this give? The greatest integer function of x plus y equal to n plus m plus 1. Why does this? Because if mu1 mu2 are less than 1, but they have some value, but we will get mu1 plus mu2 is what? Less than 2. So if it is less than 2 but greater equal whom? 0. Greater equal 0. So due to this we get, or this gives the greatest integer function of mu1 plus mu2 is how much? 1. So here we can put 1. So if this is 1 or this is not exactly equal to, while this is less equal. It is less equal, that part. Fine. So this is less equal. This gives x plus y, greatest integer function of x plus y will be this greatest integer function of x plus greatest integer function of y plus 1. Call it as equation number 3. Therefore, from 2 and 3 we get greatest integer function of x plus greatest integer function of y is less equal greatest integer function of x plus y is less equal greatest integer function of x plus greatest integer function of y plus 1. This is our proof here. Now let's see the next property. Greatest integer function of x plus m equal to greatest integer function of x plus m for every m in set of integer. So proof of this, let m be any integer, m be any integer and x is a real number. Therefore, x equal to greatest integer function of x plus mu, where mu is lies between this. Fine. That is x equal to n plus mu, where mu having the same range and n is what? Set of, n is from set of integers, suppose. Fine. Therefore, if we add m on both sides, I get x plus m equal to n plus m plus mu, where this m is any integer and 0 less equal mu less than 1. Here since greatest integer function of x is what? N. This is also needed. Now here if I take greatest integer function of x plus m, then I got it as n plus m, because here here it will be, this is a fractional part, it lies between 0 to 1, so this is simply this part. Now this n is nothing but this, so greatest integer function of x plus what? M. So this can be written as such. Fine. Now let's see the next one, fifth one. Greatest integer function of x plus greatest integer function of minus x equal to 0 if x is an integer and minus 1 if x doesn't belong to set of integers. So let's see the proof of it. Okay. Let mn be any integer and x is a real number. X is a real number. Okay. X is a real number. Therefore, x equal to a greatest integer function of x plus mu, where 0 less equal mu less than what? 1. Okay. Less than what? 1. Okay. Now that is x equal to what? N plus mu. 0 less equal mu less than 1 and n belongs to set of integer. Therefore, minus x equal to minus n minus mu, where minus 1 less equal minus mu less, strictly less, sorry, this is, and less equal what? 0. N belongs to set of integer. Okay. Now, this minus x can be written as minus n minus 1 plus 1 minus mu, where 0 less equal 1 minus mu less than 1. Due to this range, I have been added 1 here and subtracted 1. Therefore, what is greatest? Let's see this side. Therefore, greatest integer function of x plus greatest integer function of minus x. What does they? Greatest integer function of x is how much? N. And what about greatest integer function of minus x is this? This is minus n minus 1 plus greatest integer function of 1 minus mu. Now, this n and minus n get cancelled. Here it is equivalent to minus 1 plus greatest integer function of 1 minus mu. Fine. So, this is equivalent to, look at it carefully, it is minus 1 if greatest integer function of 1 minus mu is equal to what? 0. And it is 0 if greatest integer function of 1 minus mu is less than, or it is equal to what? 1. It is equal to 1. That is equivalent to, it is minus 1 if, when it is 0, if it is less than 1. 1 minus mu is less than 1. And if, when it is 1, if 1 minus mu is exactly equal to what? 1. Now 1 minus mu less than 1, 1 get cancelled, so mu is what? Minus mu less than 0, so mu is greater than 0. So this is equivalent to, this is minus 1 if mu is greater than 0. And it is 0 if mu is equal to 0. So, mu greater than 0 means x doesn't belongs to set of integer. So, it is minus 1 if x is not in set of integer, and it is 0 if x belongs to set of integer. Fine. Now, let's see the next property. Sixth one, greatest integer function of x upon m is exactly equal to this one also, where m is in set of positive integers. So proof, let x belongs to set of real number and m is in set of positive integers. Therefore, x equal to n plus mu, where 0 less equal mu less than 1 and n belongs to set of integer. Apply division algorithm to m and n. We get n equal to mq plus r, where q is in set of integer and 0 less equal r less than n. Therefore, what is x upon m? X upon m is n plus mu upon m. What is m? It is mq plus r plus mu upon what? n. Therefore, x upon m is equal to what? Q plus R plus mu upon what? M, where Q is in set of integer. Fine. Therefore, this greatest integer function of this is equal to Q plus greatest integer function of this one also. Okay. So our aim to find out this part first. So now as 0 less equal mu less than 1 and 0 less equal R less than M. Okay, M minus 1. Therefore, 0 less equal mu plus R less than 1 plus M minus 1. Therefore, 0 less equal mu plus R less than M. Therefore, 0 less equal mu plus R upon M less than what? 1. Therefore, we get mu plus R upon M having a greatest integer function is what? 0. Hence, greatest integer function of x upon M is how much? Q. Call it as equation number 1. Now, greatest integer function of x is equal to n equal to mq plus r. So, it is greatest integer function of x upon m equal to mq plus r upon m, that is equal to q plus r upon m. Therefore, this is equal to q plus greatest integer function of r upon m. Now our aim to determine the greatest integer function of r upon m. As 0 less equal r less than m, so this gives 0 less equal r upon m is less than what? 1. Therefore, the greatest integer function of r upon m will become what? 0. Hence, the greatest integer function of this upon m is also what? Q. Call it as equation number 2. So, from 1 and 2, we get greatest integer function of x upon m is same as the greatest integer function of x upon m as such. Now, let's see the next one. The next property is that seventh one. If m belongs to set of integer, positive integer, and a is any positive integer, then this m upon a, the greatest integer function of m upon a, gives the number of positive integers less than or equal to m that are divisible by what? A. So, let's prove it. Proof. Let m and a are in set of positive integer, then 1 into a, 2 into a, 3 into a, and so on up to j into a are the positive integers positive integers less than or equal to m, and that are divisible by what? A. Therefore j into a less equal m less than j plus 1 into a. Therefore j less equal m by a less than j plus 1. Okay. This gives the greatest integer function of m upon a is how much? J, where j is what? Number of positive integer less equal m, and that are divisible by a. Now let's write one more note, or you can say a small property on this. You can give a number to that one also. 8. That property is what? Minus of greatest integer function of minus x is the least positive integer, and which is greater equal to x. So proof of this: let x is in set of real number, then this is what? The greatest integer less than or equal to x. If we take this one, this is also greatest integer less than or equal to what? Minus x, and minus of this is least, opposite of it. So least integer greater than minus x or equal to minus x. So this is about the properties of greatest integer function. In next video we will see the examples on this one. Thank you.